Good morning students, welcome to second session on the Riemann integration. So in this session let us study about the theorems on Riemann integration. Take first theorem. If f is a function from a comma b to r is a bounded function and p belongs to p of a comma b, then m into b minus a which is less than or equals to lower Riemann sum LPF which is less than or equals to UPF and which is less than or equals to capital M into b minus a. This theorem is important here. This one is important. So let us take proof here where small m and capital M are infimum and supremum of f on a comma b. Let us take the proof. Let p, this interval a comma b, is equals to x0, x1 etc. up to xn equals to b, be a partition of the closed interval a comma b. Since f is bounded on a comma b, and this implies here f is also bounded on each subinterval xr minus 1 comma xr, where r is equals to 1 to 3 etc. up to n. Let us take small mr and capital Mr be respectively the infimum and supremum of f on xr minus 1 comma xr. That is, here let us take subintervals in this. So here p is equals to, we have a no, x0, x1 etc. No? Suppose here first interval here I1. I1 means here it is what here? I1 means it is x1 comma x2. Like this here IR means xr minus 1 comma xr. So I1 is this is I0, this is I2, it is like this. So we can divide this partition into subintervals like this. So here this is the rth interval is IR is equals to xr minus 1 comma xr. Now we know here this m is definitely less than or equals to mr, because here mr is the infimum of this rth interval. This is mr and this is capital MR. So small m is what here? Small m is the infimum and supremum of this a comma b. Here a is small m and capital M is b, and these are all in between values we can take here small mr and capital MR. Now multiplying on both sides by delta r, let us see, multiply each term by delta r, we will get like this here. So then apply sigma from r is equals to 1 to n to all the terms. Then we know here if you take m outside becomes sigma r equals to 1 to n delta r, and we know this is the definition of, this is what here, this is the definition of LPF we know, and this one is the definition of UPF. So which is less than this capital M into sigma r equals to 1 to n delta r. So we know sigma r equals to 1 to n delta r is b minus a. See here how it is equals to b minus a. We know sigma r equals to 1 to n delta r. So means it is delta 1 plus delta 2 plus etc. for delta n. So delta n means here this is the length of interval I1. I1 is here x1 comma x0 comma x1. We know here I1 is x0 comma x1. I2 is x1 comma x2 etc. So delta 1 means length of this interval x1 minus x0. Delta 2 means x2 minus x1 etc. it is. So all the terms will get cancelled, only xn and x0 remains. Xn minus x0, we know xn is b and x0 is a. So sigma r equals to 1 to n delta r is b minus a. So it becomes m into b minus a, which is less than or equals to LPF, which is less than or equals to UPF, and it is less than or equals to, this is capital M into b minus a. This is only the proof of this theorem. Let us take one more theorem. If f is a function from a comma b to r is bounded and p belongs to p of a comma b, then LPF is less than or equals to UPF. So again it is considered a partition p is equals to a, which is a lower bound of this limit x0 comma x1 etc. up to xn, which is equals to b, be a partition of the closed interval a comma b. Since f is bounded on a comma b, so therefore f is bounded on each subintervals also, that is xr minus 1 comma xr. Let this small m and capital M be the infimum and supremum of f on a comma b, and we know here this mr and capital MR be the infimum and supremum of f on this subinterval xr minus 1 comma xr. So here infimum is small mr and capital mr is supremum. And we know here that small mr is less than or equals to capital mr. Small mr means if infimum, this one small value. So and it is capital mr is supremum, which is greater than this infimum. So small mr is always less than or equals to capital mr. Let us multiplying on both sides by delta r. So that is here delta r is what? Length of the interval IR. So mr into delta r, which is less than or equals to supremum of this interval IR into delta r, and apply sigma on both sides here. That is sigma I is equals to 1 to sigma r equals to 1 to n mr delta r, which is less than or equals to sigma r equals to 1 to n capital mr delta r. And again from the definition we know this one is what here? LPF, which is less than or equals to UPF. So this implies what here? This implies LPF is always less than or equals to UPF. Let us take one more theorem. If f is a function from a comma b to r is bounded and p belongs to p of a comma b, then LP minus f is equals to minus UPF and UP minus f is equals to minus LPF. Let us take the partition P is equals to A, which is equals to x0, x1, etc. up to xn is equals to B, be a partition of the interval a comma b. And again same thing in all these theorems, we have to remember these points here. M is the infimum and capital M is the supremum of the given interval a comma b, and small mr and capital mr be the infimum and supremum of the interval xr minus 1 comma xr, that is IR. We can take this one as here IR. Since f is bounded and so minus f is also bounded. We know bounded means it has limits both upper and lower. So this implies here what here? Minus capital mr and minus small mr are infimum and supremum of minus f. We know since here supremum means maximum value and infimum means minimum value. So if you take minus sign, it becomes reverse. You know here 5 is greater than 2, but minus 5 is less than minus 2. So this implies what here? This capital mr is the supremum in the case of positive function. So it becomes minus mr becomes infimum in the negative function. Similarly, minus small mr is the supremum because minus means again these values are interchanged here, their position interchanged. So they are infimum and supremum of the function minus f in the interval IR it is. Again by the definition of LP minus F is equals to, we know sigma r equals to 1 to n. From the definition of this is lower sum, it is equals to minus capital mr delta r, because it is infimum of this minus F, which is equals to, we can take minus n outside, it is sigma r equals to 1 to n capital mr delta r. So and we know capital mr delta r is what here? UPF for positive function. Similarly, UP minus F is equals to sigma r equals to 1 to n here. Here it is upper m and sum means you have to take supremum. Supremum of this minus f negative function is minus small mr into delta r. So again we can take minus n outside, it becomes sigma r equals to 1 to n small mr delta r. So UP minus f is equals to, here we can take here minus n as it is, and this is the definition of what here? This is the definition of LPF. So thus LP minus f is minus UPF and UP minus f is minus LPF. That is here, if the function are negative, then the lower m and sum becomes upper m and sum and upper m and sum becomes lower m and sum. So this is the proof of this theorem. Thank you.